I'm Brandon, and I'm going to be the session chair for TA, molecules, how might we blow them up? And so your molecule was blown up, how to pick up the pieces and put Humpty Dumpty back together again. So these are the two sides of astrochemistry. We blow stuff up, and then we put it back together, and I'll give you a little introduction into how we do all that. So first, this is our lab. So astrochemistry starts when a star explodes. This is a hard reset to the chemistry. You kind of blow everything up, you atomize it, and you start from scratch. Eventually, things condense back into a cloud of gas and dust. These are usually sort of a few to hundreds of light years across, very big. Eventually, we heard a lot about this yesterday, but these start condensing down into smaller and smaller cores. For the high mass star forming regions, you get many of these. Like hundreds of these in a single cloud will condense down into protostars with disks around them. Then they condense even further. They form little planets and planetesimals. The big ones gobble up the little ones. They accrete all of the matter that was left over. And if you're lucky, for some places, you get life. And for an astrobiology conference, this is what we're really interested in, is which ones of these systems actually end up with life, and what can astrochemistry add to that picture. And so astrochemistry isn't really about any one of these places. It's not about, supernovae or gas clouds. It's about the process that happens through this. Because once you blow this up, you have to start from scratch, building bigger and more complex molecules all the way through. And that's what we study, is how you get from there to about here. Once we get to here, astrochemistry's out. This is planetary science or biology's problem. Yeah. And so for the most part today, we're going to hear talks that focus sort of on this area, mostly because these are the most easily observable places where chemistry happens in the universe. And so one of the really cool things, I think, for astrochemistry and what it can tell you about astrobiology is this. If you look at things like the Murchison meteorite or comets, you see this really awesome mix of stuff. Things like long-chain fatty acids, purines, pyrimidines, amino acids, even some light sugars that are all just, you just grind this up and extract it and it's there. And this is a meteorite that fell to Earth and successfully delivered this without destroying all of it. And this is kind of a small-scale example. We know comets can do this too, and we kind of heard a little bit about this yesterday, that the Earth accreted a pretty sizable amount of water and other organics as it was forming through stuff like this. And the really cool thing is this is a pristine record of the solar system at its earliest point. This is chemistry this is molecules that were around before the Earth even formed. And so the question is, from an astrochemical perspective, how did you make that? How do you get that there? How typical is it? What are the inventories you think you're going to be working with on a planet that's forming, and what can that do for forming life? And how does that happen? It's not aliens. It's chemistry. It's the same chemistry you learned about in Gen Chem class. It's just applied to a really weird system. So to start with, this is our periodic table. So this, everything is scaled by size to the abundance of the molecule in space. So hydrogen is far and away the most abundant thing you have to work with. Next is helium, then oxygen, carbon, nitrogen. All the interesting stuff is like 1% by number. So almost everything you're dealing with is hydrogen and helium. And for stuff we'll hear about later, the dust and ice, that is one of the big powerhouses of making more complex molecules, is only about 1% of the total mass. For the beaker, these are usually massive star-forming regions. Once the clouds of gas and dust condense, that's where you can actually start to form molecules. These have masses of tens of thousands to millions of solar masses. These are huge associations. Once you get down to the protoplanetary disks, they're pretty tiny, but for the bigger clouds, they're hundreds of light years across. These are enormous things. The densities can start off at 100 molecules per cubic centimeter, and they get higher and higher. For reference, the air you're breathing is like 10 to the 19 molecules per cubic centimeter. So in space, especially in the diffuse areas, molecules can go months between colliding with other molecules. They are very lonely. They just ping around and eventually bump into something. The temperatures can get up to 1,000 Kelvin. For most places, it'll start down at 10 Kelvin as things condense and eventually warm up to 300, which is toasty warm for the interstellar medium. And the chemistry looks kind of weird. I mean, everybody's taken Gen Chem, so if you had some equilibrium with these molecules, you'd expect it to end up on the right here. But you have to get through some intermediate, and in space, that's not always so easy. So you can't describe things by simple Boltzmann statistics. There's barriers in the way. And so the good news is that history matters. So the state of your system, when you see a cloud of gas and dust, it depends on the detailed history of what happened before it. So you can sort of measure, you can actually use this to tell you something about what happened. The bad news is that history matters, because the details of, what's the difference in energy, what's the barrier, what are the rates for all of these things are incredibly important. And if you want to figure out what the hell's going on, you have to know all of the details that went into making this to figure it out. And that's millions and millions of parameters you'd have to know. So it turns out to be really tough. And that's a lot of what we're going to hear about today, is actually figuring out the details of this so we can actually understand something about the chemistry that we see happening in space. Because ironically, for a field where you study things that are absolutely enormous, most of the stuff comes down to the details, knowing these tiny atomistic details. So the two flavors of chemistry we really work on studying are gas phase chemistry. So in these big clouds of gas and dust, you get weird chemistry. It's driven by ions like H3+ and CH3+. And you just chain things together in simple bump, bump, bump reactions. But if you want to understand this, you actually need to know something about all of the rates for everything on this page. And this is one of the simpler reaction schemes you can think of. The other one we'll hear a lot about is grain surface chemistry or ice chemistry. So once things cool down, everything condenses out into these fluffy grains of usually silicon and carbon. And so cools off, things accrete, another molecule accretes or atom accretes, and they roam around and get together and react. This actually turns out to be how you make most of the more complex molecules in the universe. This concentrates everything down, so if you're going a month between colliding with things, it takes a long time to build up anything more complex than, say, methanol. But if you put everything down on a tiny little grain of gas and dust and let them roam around together, it concentrates them, it catalyzes reactions, and you can build much bigger and more complex things. So we'll hear a lot about both of these today. To give you an idea of sort of the state of the field, this is, I think, as of a few months ago, pretty accurate. This is every molecule we've ever found in space. There's only about 200 of them. And if you'll notice, it's really heavily weighted to really light stuff. It turns out that seeing molecules 20 and 30 light years away or further is really difficult. And so the bigger they are, the harder they are to detect, not just to make, but to detect. And so what you see is, diatomics are pretty easy, triatomics, but as you get up to, and this is what we would call complex, anything over 6 atoms, it gets very difficult, and the numbers start dropping off quick. And so anybody that's reading really quickly will notice glycine's not on here. Glycine's there are no sugars on here, there are no amino acids on here. The really basic, interesting stuff you would like us to be able to tell you about, we still can't find, which is a little tough, but it means that we have to lean more heavily on things that we can do, like simulate the chemistry that makes everything here, and use that to infer abundances we can't see. But this is kind of state of the art. So just to give you sort of a brief overview of what astrochemistry ends up doing. So laboratory astrophysics, astrochemical modeling, and observational astronomy are the 3 sort of pillars of astrochemistry. We'll hear talks mostly today in these 2 sections. So laboratory astrophysics, that's where you measure spectra. That lets you interpret your results. It gives you all the parameters, or hopefully a lot of the parameters for your chemical models, kinetics, thermodynamics, cross sections, things like that. Astrochemical modeling is generally how you would interpret a lot of the results. You model the observations you see. You model them forward in time to figure out what's going on. You can use them to think about what are the likely abundances of things you can't detect so far. And then observational astronomy is sort of the stupid check on all of this. What's actually there, how much of it's there, and where is it? So a lot of the huge amount of progress has been made in the last couple of years with things like ALMA we've heard about. And so a lot of what we're going to be hearing about today is trying to figure out, interpret a lot of the observational results that already exist today. And so, yeah, this is pretty much how we do astrochemistry. All right, so that's it. That's all I've got. I just want to hurry up and get out of the way so you guys can hear some talks. Questions about astrochemistry?
Why bigger molecules are harder to detect?
Two things. One, so, I mean, even on a grain surface, it takes a while for stuff to find each other, and in the gas phase, collisions are slow. So basically, statistically, it just takes a while to build stuff up. Also, if it takes a while to build stuff up, it's much easier to tear it down. So a lot of what we'll hear about today is photodestruction. And bigger stuff, just if it takes a while to build it up, it gets blasted apart faster. Or not faster, but it gets blasted apart fast compared to how long it takes to make it. Also, heavier stuff is just the signal gets weaker because instead of just having like 2 states that are occupied for a rotational transition, you get like 2,000 states that are occupied, and you have less molecules spread over more states. It's tough to detect a single one. So yeah, big is bad, but big is good because that's where all the complex stuff is. Any more questions? Certainly, isn't it? All right. In that case, first speaker, come on up.